Good evening, everyone, and welcome to the 18th Tack faculty lecture. So it's a wonderful evening, and thank you for being here. This lecture series was established in 2012, and it was born out of a very simple idea. How can we bring focus and interest around the things that we do at the university and do not hide our light under a bushel? This light, of course, in this case, is the amazing faculty of William and Mary. I think that we all agree that they illuminate the lives of our students every day. Martha and Carl Tack, both of class of 78, saw this firsthand as students themselves. They knew that faculty members' research is important and relevant, and that their lecture styles are creative and fascinating. They saw that William and Mary needed a way to invite the public into this house so they could enjoy the same intellectual spark. And hence, the first Tack faculty lecture was held thanks to their generosity. Now, if you were paying attention, certain words were used in what I said so far, and they weren't accidental. Light, illumination, spark. They were intentional. Bill McNamara's work is centered around how to harness the power of the sun to not only generate electricity, as we've been doing for decades, but to create fuel that would help us decrease our reliance on fossil fuels. Bill grew up in the coal mining town of Scranton, Pennsylvania, which was once the world capital of the anthracite mining industry. This home and its people shaped his intellectual course. This is what he told us during his video. What really struck me were the struggles that people went through with coal and with anthracite. Seeing the human loss behind mining and the difficulties got me interested in energy in general. Bill earned his bachelor's degree from Lafayette College, where he studied self-assembled monolayers using atomic force microscopy. He went on to earn his PhD from Yale, where he studied organometallics and water oxidation chemistry. He studied a photocatalytic process for water oxidation, a key chemical reaction for the conversion of solar energy into chemical fuels. At the University of Rochester, Bill continued developing earth-abundant, metal-based photocatalytic systems for his postdoctoral work. Then he joined our Department of Chemistry, yay, in 2012. He has continued to study methods of harvesting solar energy, and he is the Wilson and Martha Claiborne Stevens Associate Professor of Chemistry. In 2018, Bill was honored with a 5-year career award from the National Science Foundation to continue his research. As a career awardee myself, I can assure you it's a great honor, and a great honor not only for Bill, but for our university as well. I had to say that I was also a career awardee. Did you notice? In 2019, he was named a Henry Dreyfuss Teacher Scholar, a research award honoring young faculty in the chemical sciences who are accomplished researchers and committed educators. I just want to say one more thing about the Dreyfuss Awards. Bill was the 9th active member of the chemistry department to hold this honor. And throughout the history of this award, and this is important, no other institution of higher learning has had more Dreyfuss scholars than William and Mary. So I'm going to let that sink for it. So the Dreyfuss Foundation made clear to the world something we already knew, that Bill is a deeply dedicated researcher and mentor. Students in his lab, some of whom I met tonight, from Canada, China, Fredericksburg, and more, use an interdisciplinary approach rooted in inorganic chemistry to develop clean and renewable energy. One of the lab's main focuses involves the development of transition metal catalysts for artificial photosynthesis. That's the pumping iron that in the title of tonight's lecture. The researchers rely on synthetic, physical, materials, and inorganic chemistry to develop systems for harvesting and using solar energy. So before I came here tonight, I was warned that I will have to use some difficult words in my presentation. I don't know if you notice how well I navigated those words. So, as you know, or maybe you do not know, most of these words are of Greek origin. So, hey, you know what? Speaking Greek has its uses sometimes. So, honestly, I was really very excited about tonight, and I still am, and I'm looking forward to the wonderful things that Bill is going to present to us. To be honest, I was promised pyrotechnics. The fire marshal was actually consultant. But anyway, so Bill has an exciting, engaging, and very relevant evening planned for us. So let's welcome him, Bill McNamara.
Thank you so much. So thank you so much, Provost Aguirre, for that kind and really riveting introduction. I really hope my talk can live up to that. But I have a couple warnings just to begin my talk, and that is, as was mentioned, there will be some pyrotechnics. So one are going to be some bangs, and there's going to be a flash at the end. So if you're photosensitive at all, I'm just giving you a warning about that. When you see me put my goggles on, that's your cue. And that's a cue whenever a chemist is doing something, that something's about to go down. And something just doesn't feel right. I don't know if it's the lights or the camera. Oh, I figured it out. Oh, there we go. So I've got a couple of things that I want to say about the talk this evening. I am here to tell you about research that I'm doing in energy, but I really want to make clear that I do not believe that what I am doing is the only thing that needs to be done to solve the energy crisis. The energy crisis and powering the planet is going to require a diverse energy portfolio. I'm hoping and envisioning that hydrogen will be a part of that, but in no way am I putting down any other sources of renewable energy or energy. It's going to be important to incorporate wind, geothermal, nuclear into our energy portfolio as we move forward. And in the short term, we're going to have to rely on fossil fuels as part of our infrastructure. So these are not things that I am putting down in this talk. And I'll mention one shortcoming of photovoltaics being batteries, but I don't mean that as a shortcoming. Battery research is very important for that reason as well, okay? So all of this is really important, and there's a lot of interesting research going on at William and Mary in these areas as well. So in the introduction, it was mentioned about where I'm from. So I'm from Scranton, Pennsylvania. It was mentioned that it's an anthracite town. You might know it as being the setting from The Office, right? And I can confirm that every single person in Scranton is, in fact, Michael Scott, and they do, in fact, sell paper. But Scranton had sort of humble beginnings. This is Scranton in the very early days. It's on the Lackawanna River in northeast Pennsylvania. And it was also a big railroad town, okay? And what was nice about Scranton and its location was that it is not far from New York City. As if you watch The Office, they end up going to New York quite a bit. It's not far from Philly, okay? So it had this interesting location, but that location was not necessarily what made it boom. So here is Scranton, not long after the picture that I just showed you. What happened? The Industrial Revolution started happening. You already know that I'm going to tell you a little bit about coal, but what was driving that coal initially is Scranton was a big steel town. And at the time, they needed coal for that steel, okay? And so that really drove things, and steel ended up dwindling out a little bit in Scranton, but coal was powering the country at the time. and our war efforts in the world wars, and it became very important, okay? And so that gave Scranton this boom. It's called the Electric City because it was one of the first cities with electric streetlights and trolleys in the country. And if you ever visit Scranton, there's a trolley museum commemorating this. I guess I recommend it. It's interesting nonetheless, but this is why Scranton boomed. And so that was one of the reasons that I got into this, and that was because, as was mentioned, it's a coal town. And Scranton's all about anthracite coal, which is a more expensive type of coal. It burns very hot. I actually have some with me that I'm going to share with you. So I'm coming down. They're rocks. I have them in bags because coal is dirty. But if you open it, it's going to get all over you. They're in bags because I don't want to ruin Sadler. And I'm not going to throw them at you because they're rocks. And I don't need assault charges after the Tack lecture. So. Sorry. Yeah, it's like Christmas at the McNamara house. It's bringing back all these memories. Oh, you got a big one. Yeah, so this is what was being mined out of the earth, and it's very dirty, and you're going to see that. You can hold on, Lisa. I don't want the coal back. Thank you, but I'm good. Yeah, Merry Christmas. Oh, you save it for Christmas, you know? I will also mention that my son is here. He is 5 years old, so Seamus. You can add one of these to your rock collection when you get home. Always come bearing gifts. Handfuls of coal. I really wanted to throw them, but I thought better of it. Yeah. Bam. Nailed it. You want me to throw one? You got this? Nice. So unfortunately, I don't have enough coal for everybody. It turns out that anthracite is very expensive, and that is true. That's one of the limitations behind anthracite. But we're going to get into that a little bit more. One thing, the images that you're looking at here are reminding me of my childhood, okay? I did not grow up in Virginia. I imagine that if you did grow up in Virginia, your middle school and high school field trips look something a little different than ours did in Scranton. You might go to Monticello and see the home of Thomas Jefferson. You might go to Colonial Williamsburg and learn to make bricks. We did not do that in Scranton. We had coal mines, so what we would do is we went to the Anthracite Coal Museum. And in that museum, it doesn't sound terrifying yet, but I was probably, 8, 10. They load you into a coal car at this anthracite museum, and you go down into an old coal mine about 200 meters. Okay, and there are some animatronics, and some of them work. They're not exactly Disney level, but they're terrifying, and there are animatronics of canaries in cages going like this. So it really conveys sort of what these miners were up against, right? And then after the field trip, we would go and get pizza at Alfredo's Pizza Cafe. Not pizza by Alfredo's. They were right about that in the office. It's hot garbage. That's advice if you're ever in the area. But that was sort of what it's like. And that sort of got me thinking about this, because there were other things that came up when we were at the Anthracite Museum that caught my attention. And one of them has to do with the fact that my son is here and I'm now a dad. What was sort of interesting at that Anthracite Museum is they had children, and they had children who were ages 8 to 14 working the mines. They were called breaker boys. Seamus, you're 5, buddy. So you would be 8 when you worked in the mines. So how many more years would that be? Can you hold your fingers up? 3? Someone learned something at my Tack lecture. This is amazing. Good job, buddy. Yeah, that's right. So he would be in a couple of years going off and doing that. And what that looked like what you're looking at physically in this photo is you're looking at these young boys, and in between their legs is flowing coal. It is coal, it is shale, and they're picking out the shale with their hands, okay? And this would obviously bloody some of the children. They would get cuts and things like that. They would work over 12 hours a day. So conditions were really grim, and they were breathing in all this soot. If you didn't listen to me and you opened up your bag of coal, you know what I'm talking about. It gets everywhere. So there were these conditions, right? And out of this came some really interesting things for our country. The idea of having child labor laws was an important idea, right? That this is no longer acceptable to do, and things like this. But that was very harrowing, and that's what I was mentioning in that video when I said about the human loss of coal mining. We often overlook that, and we focus on solely emissions from fossil fuels, but the history of it is so interesting, and it's so interesting culturally as well. And so another thing that I want to mention is that there's an environmental impact behind the mining of coal. And you might not see this in Virginia, in this part of Virginia, but in Scranton there are these mountains, and they look like this. And you wouldn't think anything of them, right? They're called culm piles or culm dumps. And what they are is they're the undesirable coal products from the mine, and they just layer them up into a mountain, and that's big. And I thought it was so cool at the time because people would ride their dirt bikes up and down them. How cool was that? Except they catch on fire, okay? And if you don't, it's hard to ignore something environmental that's going on when a mountain next to your house is on fire from coal, right? It's hard to ignore that. You're breathing in those fumes. You're literally staring at this, and they smell. And I don't know that dirt bikers were the ones who were starting these fires. I'm not saying that. They actually used to think it was from lightning strikes or something like that, but I think more recently they found out that's most likely due to people burning trash and embers going through the air and lighting them on fire is what the current thought is with why these catch on fire. And if you're thinking like, oh, that happened in the 50s, we're good. This happened recently in 2016 in Scranton where a culm pile was on fire. Okay, so this is a problem that people are still dealing with as a result of mining. Another example that I like to bring up is we weren't too far from this town, and it's a very interesting story. And that is this town of Centralia. They had these mines because they were also in the Anthracite region. They were also mining coal, and what they did was they didn't properly seal off the mines. They didn't know that at the time, but there was a Memorial Day parade, and they wanted to get ready for that Memorial Day parade. They had a landfill, and that landfill was big, and they didn't want it as the backdrop of their Memorial Day parade. So they lit it on fire. Why not? And they did it in what they thought was a controlled way. They had the firefighters doing that and watching it to keep it contained, but it ended up setting the mines ablaze underground. And what happened as a result of that was the mines caught ablaze underground. And then you had these sinkholes opening up. And initially, the people thought, it's that classic meme of everything on fire and this is fine. That's what people thought. They're like, this is fine, until sinkholes started opening up and people started falling into them. Now, I think there's only 5 people left in Centralia. The government has relocated people a long time ago. And most people have moved on. But even today, if you go to Centralia, you're not supposed to, it's blocked off, doesn't have a zip code, you will see smoldering roads and just random piles of smoldering things just on a walk. It's really harrowing. So now on to what I'm doing. So this really inspired me, and another thing that inspired me is my great-grandfather was a coal miner. But people were aware of what was going on and the limitations of coal, even when coal was booming, okay? This is a famous photochemist from Italy of Armenian descent who is writing in the journal Science about coal in 1912. And this was such an interesting paper to me. And I'm going to not read you the whole paper. I'm just taking an excerpt out of it. But if you're interested, the citation is there. It's really interesting. because he came up with the groundwork for what I'm about to tell you in 1912. He came up with this idea of artificial photosynthesis, which I'm going to talk about. But what I want to tell you about what he actually said, because I think this is so fascinating about how he referred to it. He says, modern civilization is the daughter of coal, for this offers to mankind the solar energy in its most concentrated form. That is, in a form in which has been accumulated in a long series of centuries. Okay? They knew it took so long to make coal. Modern man uses it with increasing eagerness and thoughtless prodigality for the conquest of the world, and, like the mythical gold of the Rhine, coal is today the greatest source of energy and wealth. But what he goes on to say, the earth still holds enormous quantities of it, but coal is not inexhaustible, okay? And that's the point. And then he goes on in this paper to talk about artificial photosynthesis and some really cool photochemistry, but that stuck with me. People in 1912 knew we were going to run out of this, okay? And that's the reality of fossil fuels. They're very precious. I handed you out coal not because I dislike fossil fuels. I handed you coal because it's precious. So this is our current energy portfolio in the United States, and I want to bring your attention to a couple of things here. One of them, a couple of encouraging things. This is not a doom and gloom talk. We've had a lot of that in the last 2 years. We could use some positive thinking here, and there is positive thinking here. And you'll notice from 1950 to 2020, we're using in the United States much more renewable energy. That is good news. And our energy portfolio is becoming more and more diverse. And you can see, too, that over time, coal use went down, especially recently. As we shift, and it shifted basically more to petroleum, and that has shifted to natural gas. But what I want to point out here is how little comes from renewable energy. And I think that's going to change. I think we're moving as a globe and as a country to making this a larger slice of the pie, and I would really like to see that. And I'm going to tell you about how we're thinking about doing that in our lab. Okay, let me see, make sure I didn't skip anything. Okay, so why solar energy? Couple of reasons. One is it's so abundant. This is a positive of solar. I don't speak terawatt. I don't go around talking to people in terawatts. But to put it in perspective, about 23 to 25 terawatts of energy is consumed globally per year, okay? And that's maybe a little different. The last couple of years with COVID, things are a little off trend, as you can imagine. But that's generally true. And 1.2 times 10 to the 5th terawatts of solar energy is available for us to use. That's orders of magnitude greater than what we use, okay? And so that's important. There's a lot of potential there. And just looking at that, people have done the math that enough sunlight strikes the Earth in 1.5 hours, then we actually use in energy for an entire year. So that kind of puts that 1.2 times 10 to the 5th terawatts into perspective. And here I also say, and I'll talk to you more about this, it can be harnessed and used for fuel. Plants have figured this out without giving Tack lectures. They're really creepy. They have just figured this out over time, and they're very good at it. And we have figured out how to use it, how to use solar energy to make electricity, okay? And you can think about your photovoltaics that you would have on a house or something like that, those silicon solar cells. And also if you use solar, it alleviates some of the political environmental drawbacks of oil, environmental being oil spills and things like that. Political meaning it would be good for us to have energy independence, and that's what I'm saying there. Okay, this is just for fun. So this is concentrated solar energy. This is another type of solar energy. I find it sort of interesting because I met one of the engineers who worked on designing this at a conference. And what this does is there are all these mirrors, and they shine up, and so it concentrates the solar onto a tank, and that tank has water in it, and that water will boil, and you'll make steam, and that steam will power a turbine to make solar energy. So it's basically the spire of Mordor sticking up, and there's an eye there at all times. There is a limitation there. You need sunlight. You need to be somewhere sunny. Also, birds are a problem here. I'm not going to inappropriately tell you why, but you can imagine why birds might be a problem for all these mirrors. We all have cars. So that is pretty cool, but the person that I met, that engineer, I asked him, so how did you guys come up with this idea? And he said, you know when you have magnifying glass as a little kid and you concentrate the sun and you just blast ants? And I'm thinking, this is my response. Yeah. But it was just so interesting. He was joking, of course, but it's just another way to do solar energy that you don't often see. We do have a limitation here, and that is clouds. So this problem can be sort of helped out by storing things in batteries. So battery research is very important. Batteries come with their limitations in that they can be expensive. They have been getting less and less expensive over time, which is fantastic. But there are also some efficiency losses and things like that. So clouds can be a limitation for us. So what I wanted to do and what I thought I could do is make a cloud for you all. This isn't the cloud. This is not the cloud. So we just have to get this in there. The suspense must be killing you. All right. Let's make ourselves a cloud so I can show you how they can block out some light. In case you didn't know that clouds can block out light. Hey, I have to tie it in. All right, here we go. That'll work. Thank you. Yep. Okay, thank you. Thank you, Tim and Jake. All right. So we made a cloud. Clouds can be a challenge for solar energy. Another challenge is that it's diffuse. So I didn't ruin any technology. This is good. Okay. Another limitation, or not limitation, but yeah, limitation. It's not sunny all the time. So I already kind of mentioned to you what we do when the sun's not shining. There are two things if you buy photovoltaics for your house normally. One is you can feed it right back into the grid. And then when the sun's not shining, you're getting your energy from the grid. That is one way to do it. That works great if you live somewhere with a grid, okay? There's a large part of the country, and some parts of our country, that don't have a grid or a reliable grid, okay? And that's an important point of this image here. This is, by the way, this is taken on a rare day. It's one day every year where the entire globe is dark at once. I'm just kidding. But I put this up here for a reason, and because it highlights something. It highlights who's using the energy when you look at the Earth at night, who's using a lot of our energy. And some areas that might get brighter and brighter over time, developing areas that have population centers that are going to be using more and more energy. And so we're going to need to come up with ways to power those areas, okay? And that's what I'm going to talk to you about. So I already told you, I alluded to this, that plants have figured this out. It is creepy that they have done so, but they do a very good job at it. They take CO2 and they make sugar, and they take water and they make oxygen, okay? And this is through the process of photosynthesis, and this is going to convert sunlight into stored chemical energy in sugars, okay? I don't like sugars as a fuel, so I'm going to tell you something a little different, a different approach in a second. I think about this as a chemist because I'm a chemist by training, and I would refer to this as a redox process, where I have an oxidation reaction and a reduction reaction, and I'll show you more about that in a second, okay? My wife is a biochemist, and she's a professor at Christopher Newport University, so I had to throw in this slide of some biochemistry. This is what photosynthesis actually looks like if you look at the proteins. To me, it looks like Lovecraftian horrors reaching through a membrane, but it's not. They're very important proteins. They're very intricate. And you can see you have photosystem 2, which is a monster. You've got basically electron transport chains. You see now you have me talking like a chemist. And you've got photosystem 1. This is how I think about it. This is how I strip that down and think about it like a chemist. What I think about are those two redox reactions, okay? I think about one reaction being the oxidation of water to oxygen, okay? That's at photosystem 2 from the oxygen evolving complex. The reduction comes in photosystem 1 of NADP plus to NADPH. And this is an electron transport chain, some of those beautiful proteins that you saw there. That will no doubt give me nightmares. But what I'm thinking about doing is, okay, if I look at how nature does it, how can I model that to make a fuel that I can use with our infrastructure, okay? And to me, hydrogen is really attractive in that way. Hydrogen's attractive in a couple of ways, which I'll mention in a second. But what I was thinking that we can do is if we just block this off, so electrons would be coming from that oxidation reaction, and as a chemist who does electrochemistry, this makes sense to me. We would refer to the oxidation reaction as happening at the anode. Electrons would go from anode to cathode, like we teach in our general chemistry classes, to give an electron here. If I chop this in half and just focus on hydrogen, I'm going to need a source of electrons to make that happen, and I'll tell you about that in a little bit. So I wanted to tell you a little bit about artificial photosynthesis and what some ideas behind it are, because it's not just hydrogen. This figure here is from the Joint Center of Artificial Photosynthesis, which is a partnership between Lawrence Berkeley National Lab and I believe the other headquarters for the centers at Caltech. And this is their sort of idea, how they're envisioning this working. And they basically have three things that they're working with. One of them is fixing ammonia to fixing nitrogen to ammonia, reducing nitrogen. That's very hard. Nitrogen gas is very stable, okay? But ammonia can be used for fertilizer. So if you can do that, then you can have more biomass, okay? You could do more things that way. Another thing they want to do, and we're talking about emissions and CO2, I'm not talking about emissions and CO2 and climate change because for scientists that's pretty worked out at this point. There's nothing really new there to tell you. It's accepted. And what we can do with CO2 is, well, why don't we, if we have CO2, do something with it, right? Why don't we have a chemical reaction where we can do something with that CO2? We can make a fuel, okay? So can we reduce carbon dioxide? And the other thing that we can do is make hydrogen gas from water, and I'll tell you about that a little bit more. And then the hydrogen gas can go into fuel cells, which are used to generate electricity. They can go on to hydrogenate CO or CO2 to give you chemicals, fuels, if you wish to go that route. Fuel cells will give you electricity directly. Burning hydrogen will just give you water as a byproduct, but I'll tell you about that in a second. Okay, so why hydrogen? Hydrogen is stored in water, in hydrocarbons, and organic matter. It is pretty energy dense. It has 1 kilogram of hydrogen has about the equivalent, don't put that there, of 2.8 kilograms of gasoline. And hydrogen burning in fuel cells produces only water as a byproduct. Here's your boom. Woo! Hydrogen works. Do you? Yeah, you do. Woo! Okay. Don't put that there. All right. So you can see that hydrogen, when you burn it, I don't think you need it. Yes. But yes, you get energy when you burn hydrogen, and the byproduct is water. There's no CO2 emitted from burning hydrogen. Apologies about the single-use balloons. So you can also use a fuel cell. You don't have to burn it. A fuel cell, what a fuel cell does is I'm going to tell you about water splitting, something hard to do electrochemically, and that is to take water and break it into hydrogen and oxygen, its elemental components. If that's hard to do, the reverse reaction should give me energy thermodynamically, and that's the idea behind a fuel cell. That's combining hydrogen gas and oxygen gas together to make electricity and water, okay? And that's not new. Okay, hydrogen's been used a lot. It's been used a lot in space exploration, and I found this to be very interesting. This is courtesy of my master's student, Jessica Cropley, who is very interested in NASA in general and the Virginia Space Grant Consortium, and just very interested in hydrogen and the history of hydrogen in general. And it was interesting for me reading about how fuel cells were used for the Apollo 11 mission to the moon. They provided power for the command center and also drinking water for the crew. Because I just mentioned to you that hydrogen and oxygen coming together, which they already had on board, right? They're using hydrogen for rocket fuel. They're using oxygen because they have to breathe. So they already have these things. They combine them. They can make electricity and clean water. And so that was great on the Apollo 11 mission. Okay. I'm here telling you about hydrogen. Problem solved. You guys have been hearing about hydrogen economies forever. Like, why isn't everything hydrogen already? There are challenges, okay? Like I said at the very beginning of my talk, I'm not telling you that it's the solution to everything. There are problems here. Hydrogen is difficult to store. So research into hydrogen storage is a very critical area of research in chemistry and engineering right now, and other gases in general as well. It could be expensive if you're using fuel cells. We also do fuel cell research in my lab. I'm not going to be talking about that tonight, but it can be expensive. And currently, this is important to keep in mind, especially as fuel cell cars are marketed and things like that. And they're marketed as green. It's green. You're just getting water. You're getting electricity. It's a green car, very efficient, 75% efficiency. Where's your hydrogen coming from? A tank is what you think. But where it's really coming from, and where it's coming from, most of it industrially, is fossil fuels, okay? And so that's important to keep in mind, that usually most of it comes from steam reforming and the water-gas shift reaction with natural gas, okay? So that's where most of our hydrogen comes from. So it's important for us to find a renewable way to make hydrogen, okay? Because that'll drive down the cost, and it'll also just make it more sustainable as well. So bringing it back to what I was talking about, that sort of sets us up for what I want to do. I want to make hydrogen gas not from natural gas, but from water, because it's an elemental component of water. And that's the plan, okay? And so this is a video. People have been working on this for a while. This is from the Natural Renewable Energy Lab. I call it, will you work? Yep. I call it the solar toe. But what you're seeing, actually, irradiated with light, no bias applied, you're seeing hydrogen gas bubble off that toenail. It's not a toenail, it's a semiconductor. And it has another electrode that's making oxygen as a counter electrode. But they were focusing on the hydrogen in this one, and that was a really great result. So I'm going to be talking a little bit about inorganic chemistry and talking about metals for a little bit. And I want to just give a very basic slide to people who might not know much about metals or how metals react. I'm going to be talking about iron. And in my title slide, you saw that I was cheeky, and the title was Pumping Iron, not a weightlifting talk. That iron is going to react differently than our iron complexes, and that's what I want to talk about. So if you have iron, and you bind things, which I'm going to refer to as ligands to that iron, that's going to change the reactivity. That's going to form a metal complex. And that's going to have different reactivity than iron metal solid is going to have, okay? And that's the sort of point that I want to make here. From biology, because you'll notice that from my talk, I am very inspired by biology when I do my research. And these are some examples from biology. This is from nitrogenase. This is the iron molybdenum cofactor. You'll notice a couple of things. The ligands around it are other irons and sulfurs, and there's this one weird trick. Organic chemists hate him. There's a 6-coordinate carbon in the middle of that. Sorry. So if you write that on your exam, you can be like, but nitrogenase. Don't draw more than 4 bonds to carbon if you're outside of nitrogenase. What the point that I'm trying to make here is not that, but it's that this can reduce nitrogen to ammonia in biological systems, okay? And it's going to do that quite well with the ligands around it. This is iron and hemoglobin. This is the heme ligand around it, and that looks very different than the ligands around this, okay? So this reduces nitrogen with its ligands, and this carries blood around your body. This can't reduce nitrogen. This can't carry oxygen around your body. So based on the ligands that are around this metal, and iron is Fe, so you're going to see that as we move through my talk, they have very different reactivities, and that's sort of my point here, okay? And so our goals at William & Mary, we're trying to find an efficient way to generate hydrogen gas from water. We need to find new and active catalysts. We're going to test these electrocatalytically. I'm not going to dive too much into electrochemistry. But what I want to do is not just stop there with that academic exercise. I want to take a step towards making an actual device, okay? And we're going to see how we're sort of moving in that direction. So when I'm thinking about designing a catalyst, what do? I run right to platinum and iridium because they do a great job with this, right? Yeah, they do. But the problem with platinum and iridium, this on the y-axis is the abundance on Earth of these metals. Here's iridium, here's platinum. A lot of the iridium that we have on Earth came from an asteroid impact. I am not excited to wait for another asteroid to hit us to get more iridium. And there's a reason why none of you have iridium in your blood carrying oxygen around. We didn't have it when we were evolving, right? And so what did we have? Well, you already saw it, and I think you know where I'm going with this. Iron is the most abundant transition metal on Earth, okay? And so from a practical standpoint, if I really am being genuine about wanting to make a device, it's going to be more feasible for me to use a more abundant metal, okay? And so that's what we want to target. So other people have done a lot of great work in this. I'm not going to point out specifics here. But one thing I do want to mention to you is one thing you'll notice about these complexes is they all kind of look similar, right? They've got multiple irons, these bridging sulfur ligands, and they look sort of similar, these catalysts that other folks have created or developed. Why? Well, they were inspired by nature too. So in nature, there is these enzyme called hydrogenase. Here we have an iron-iron hydrogenase, and we have an iron-nickel hydrogenase. And you can see how that structure is similar to the catalyst that I showed you before. So they were trying to mimic those hydrogenases. The problem, so it's solved, right? They made these catalysts, we're done. These catalysts have problems. They don't work in water. They're not stable in water. So if they're not stable in water, and what I want to do is split water, that's going to be a problem, right? So where we turned our attention, similarly to those folks, we looked at a different hydrogenase, though. We looked at iron-only hydrogenase, and that's this. I'm saying this lovingly. Underneath this spinach is the active site, where the metal is that's doing all the fun stuff. And so I can make this in my lab. I can make this complex. Problem solved. Tack lecture over. McNamara out. No. So I'm joking that spinach, but it turns out you need that biological spinach around it. If I make, this is not shocking to a biologist or any biochemist, of course you do. But if I make this, and I can, it's not stable on the lab bench. It decomposes. This beautiful orange crystal turns to black in front of your eyes. It's very sad. So you need that around there for a couple of things. One is stability and those aqueous solutions that life takes place in. Aqueous just means in water. And the other is to shuttle protons in and out to do this reaction, okay? And so our approach was, I wanted to hug iron. I wanted to hug iron more. I wanted what we call a multidentate, which comes from Greek, to grab onto iron and hold it tightly. So I've got 4 arms on this iron, a nitrogen, nitrogen, oxygen, and a nitrogen, okay? And that's going to hold that iron tightly and make it more stable, okay? And then I have these chloro groups which can come off and on, and that's where the magic's going to happen in the catalyst. So we actually, this is the first complex I made, and we actually solved this structure, this crystal structure at William & Mary with the help of Professor Bob Pike. And so that was very exciting that students were able to see that and how that was done. But also it worked. And so that was really exciting, right? And so this is the catalyst in water. We're looking at this technique that we call cyclic voltammetry. I will just tell you, very basically, if you see a brontosaurus head, that's going to mean that we have hydrogen, okay? So when we see these peaks, these current enhancements, that's indicating to me that we have hydrogen generated. And I can verify that by parking a potential right here and just focusing on that potential. And over time, I should generate charge then if I am making hydrogen. And the cool thing is, if I cap off my reaction vessel, I build up hydrogen over time. And I can test it to make sure that it is actually hydrogen in something called a GC, okay? And how much hydrogen I have. And so I was able to verify that. And this is us doing that. And you can see we're making hydrogen pretty linearly over time. Hooray. It was confirmed by GC that it was, in fact, hydrogen, and our Faradaic yield was 99%, which was very exciting to see. We also, this is a serendipitous discovery, as much of science can be. We've made a bunch of these. This is one of my favorites because of the serendipity. But we're after this sulfur-containing ligand because we just thought, okay, maybe it'll be a better catalyst for reasons that we had discussed with hard-soft acid-base theory. But this reaction had to be done very air-free because sulfur oxidizes, and there's oxygen all around us. And the students did it very air-free, very meticulously under argon, made and synthesized this ligand, which is a pain. And I was confident that they did it under argon. We were ready to solve the crystal structure, and we found this. We found that it had oxidized. And I asked, how did it oxidize? You were so careful. And they're like, yeah, we were. But then we just popped open the flask, and we just did the crystallization under the air, and I'm like, aha. But what was serendipitous about this is this doesn't look right, right? Just looking at it, even if you don't know anything about or little about inorganic chemistry, this is a pretty big loop here. And so this is going to come off and on really easily and going to give us a more active catalyst, and it did. And so we made a bunch of these. IC over IP, the higher that is, the more active the catalyst is. Overpotential is a measure of activity. The lower that number, the more efficient it is. So we made a couple of these. And then what we wanted to do is we wanted to see if we can actually do this with the sun. I'm telling you about solar energy, and I've just been talking to you about electrochemistry, and no one is questioning me. Well, we're getting there. We're using that electrochemistry to see if we can get this to work. See if we can get something that will absorb light and can give an electron to our catalyst, okay? And to any photochemists in the audience, I apologize. This is probably the most boring chromophore of all time to you. But we were able to do this with fluorescein because fluorescein is reducing enough for us. Here's our sacrificial source of electrons that I mentioned, and we can pair that with our catalyst. So the chromophore is going to absorb light. It's going to give an electron to our catalyst, which is going to generate hydrogen from water. And then our electron donor is going to dump electrons back in. And if we weren't just focusing on hydrogen, these electrons wouldn't be coming from a donor. They'd be coming from a water oxidation reaction. So why fluorescein? Well, I just told you that it can reduce the catalyst, so that's obviously an energetic need. It's also really inexpensive. So this is, I always tell people this in class. This is them dumping dyes into the Chicago River during St. Patrick's Day. They've been doing this since, I think, 1956. They used fluorescein back then. They claim to not use fluorescein, but man, does this look like fluorescein. It's a red powder that turns into a green powder when it's dissolved at that pH. They say their dye is made from vegetables. I can't find what it is. So if you're from the Midwest and know what the dye is, let me know. But they used to use fluorescein. And fluorescein is used for other things. It's that dye they put in your eyes at the eye doctor to take a look at the contrast. It's also used to detect leaks in pipes and things like that, and to dye things green. Okay, this is our setup in our lab. When you come to a lab and when you first start up, you spend money on things sometimes that you just have to really budget and think about what you're doing. And so one thing that I wanted is something like this. So this is our fake sun. These are LEDs that are going to illuminate my samples. The samples are right here. They rotate, and I needed a motor. And the motor that I could get, a slow-spinning motor for a chemical company, was $3,000 to $5,000. And that just didn't seem right. Could I afford it? Yeah, but it just didn't seem right. And I had a student come up to me and say, you know what, why don't we just get some EDM ball spinners? And I was like, what? And I didn't want to seem like, out of the loop, so I kind of did some digging, and she meant disco ball motors. And so we now are lined up with EDM ball spinners in my lab. Disco ball motors are $40 on Amazon, and this rotates my samples nice and slow. Sometimes you have to improvise. We're going to, when we irradiate this, we generate hydrogen over the top of those flasks. We can take a sample with a syringe of that gas, inject it into our GC to show us how much hydrogen we have made. And each one of these points is a point that a student has injected. So what you're seeing here is our real-time generation of hydrogen. And each point is a physical point. So you can see I care about my students, and they sleep. So what you're looking at, too, there's ton. I wish that meant ton. I wish that meant that we were making tons of hydrogen. I don't know what that would look like actually for the lab or our fluorine structure. But what this means is turnover number. And turnover number is the amount of hydrogen you're making over the amount of catalyst. So the higher the number, you're better, because a catalyst is kicking around in a cycle, right? So the more times that catalyst goes through the cycle, the better you are, the more hydrogen you're making. So all of our stuff worked, all of our different complexes. This is true with my life. I reasoned through how these would be better, and I had energetic ideas, and I made these arguments, and the first thing I discovered was the best one. So is life, right? So what was interesting about this, I was mentioning the developing world, and it has a lot of potential to have an impact there. If you think about people who might not have clean drinking water, you can provide energy and you can provide clean drinking water. So if I'm going to go around and I'm going to talk about this, we need to put our money where our mouth is. So during the Zika scare years ago, we went out, we took some water from Lake Matoka here, what we did is there are some particulates in water, and if I'm making an argument about the developing world, some places don't have $20,000 filtration devices to filter out the water. It's not that expensive, but you know what I'm getting at. They don't have fancy filters. So we filtered it through a t-shirt, and we used that water, and it worked. It didn't work as well, but we made hydrogen. I will tell you by visual inspection that there were still chunky things floating around. I apologize that there are probably microorganisms that were harmed by being irradiated in this process, RIP amoebas, but it worked. And this is just a summary. They worked. We were getting about 2,000 turnovers, which is really great, the highest people had seen for iron. So okay, problem solved, Tack lecture over again, right? Not quite, because we were up against this other problem, and that is diffusion. So in this thing, this is a really nice cartoon, but in order for this to work, that chromophore has to smack into the catalyst, okay, in order to transfer an electron, and that's a problem that's diffusion. It has to wait until it hits, or get close enough, if you're following Marcus theory. And so that's a problem for us, and we wanted to get away from this and wanted to move towards device building by trying to immobilize our catalyst on surfaces. People have done a lot of work immobilizing catalysts on surfaces. One of those surfaces is carbon nanotubes that people are using for devices. It's a popular semiconductor. A lot of work has been done on it, especially for electron transfer and electrode materials. And here you can see this is going to be a pi stacking interaction. It's going to be an adsorption. And you can covalently attach them as well, and this work from Fonikov. So people had done that. But I was also interested, and this stuck with me for my PhD, in titanium dioxide, a metal oxide semiconductor. Why titanium dioxide? It's really inexpensive, okay? It's a semiconductor that's really inexpensive. It's basically titanium's form of rust, okay? And it's everywhere. White paint is titanium dioxide. It's in toothpaste. It's in sunscreen. It's in Doritos. I haven't figured that one out yet. If you know why, just tell me. It's also the white powder in powdered donuts, which objectively, I think this is going to be an unpopular opinion, is the second best flavor of donut holes. So we were interested in TiO2, and people had worked out a lot of binding chemistry on the surface to immobilize things. And so here was our cartoony idea, all right? I was thinking, all right, we might need a beefier chromophore than fluorescein. I don't know how we're going to get fluorescein on the surface. So let's use this ruthenium complex that I know will attach. We'll attach our catalyst somehow. And so how we attached our catalyst, we made this ligand. And what I was thinking is I would just make it, and then I would crystallize it, we would analyze it, and I would put it down on TiO2, and that would be that. That would be the best case scenario. But it didn't happen that way. We ran into a snag. When you run into a snag, you have to work around it. And so what happened was, when I was using this ligand, this part of the ligand, what we call a phosphonic acid, binds to iron too. So I was binding iron here, like in my original catalyst, but it was also binding there. So it's getting this polymeric mess. And it wasn't working out. So what we thought to do is, why don't we use titanium dioxide as a protecting group? And so if I put my ligand on titanium dioxide, that phosphonic acid will reach down and grab the titanium dioxide. And it's going to leave a hand up to grab onto that iron. And that's exactly what we saw. We were very happy. I told you that titanium dioxide is in white paint, and it's white. It's a white powder. So when we saw that our purple catalyst was assembling on the surface of TiO2, we were very excited. And if you can't tell that it's purple, by ocular spectroscopy, here's some UV vis that show you it's got a very similar maximum absorbance to our complex. One thing that inspired us is some work from my colleague, Professor Kristen Wustholz in her lab, where she did a lot of stuff with xanthines and how xanthines can interact with the surface and absorb in different stacking ways. And I was thinking, well, can fluorescein do that too, or even bind through the carboxylic acid, which still makes me, that's this thing, still makes me a little nervous, but it worked. And so that was able to absorb. So we thought, oh, we might have something here. So we put it all together. We put our catalyst on the surface of titanium dioxide, and it was more active than our homogeneous system, that system that I told you before, which was everything dissolved. Okay? And you can see TiO2, I think, is in red. We're making about 6,000 to 7,000 turnovers compared to 2,000 for the homogeneous system. But what was really cool about this, and this is that step towards the device that I was telling you, I can have these nanoparticles making this hydrogen. I can take them out and I can reuse them, okay, with the catalyst bonded on there. So when it stops, what's happening is the fluorescein and the sacrificial donor are decomposing. If I add the fluorescein and sacrificial donor back, which I did right here, it picks up at the same rate, okay? So these catalysts are indicating that they might be pretty stable, reusable, recyclable, and that's going to be an important step for us. Back to that carbon nanotube question, we've just recently started with this. In this case, I don't have to worry about competing binding like I did for that. We designed a ligand that could be immobilized on the surface of our electrode through pi stacking, so I can actually make this complex and isolate it and fully characterize it and have a nice crystal structure, know that it's super pure, and then put it down on the surface. And it works. It works, it generates hydrogen, it's stable to water. This is a very exciting result for us, and we're currently working through a lot of interesting chemistry with our system on carbon. And I was mentioning carbon nanotubes, and you might have noticed that my electrode, it just says electrode. We're using a glassy carbon electrode. And what this is it's basically, it's a model system for a graphene electrode or a carbon nanotube or something. It's sp2 hybridized carbon to pi stack. Worked. And so that brings us to our conclusions. And what hopefully I've been able to convey to you tonight is that iron NNNO complexes, which is what I've been telling you about, are active electrocatalysts at modest potentials for iron for generating hydrogen gas from water. Also, this polypyridyl ligand set is highly tunable. You can make a bunch of these, and you can tune the efficiency and activity, and they're not very difficult to synthesize, which is an important point when you're thinking about making a catalyst, because it's not just the metal that's expensive sometimes. They can operate in organic or aqueous solutions in water, which is exciting, because like I said, if you want to be splitting water, it's good to be operating in water, or at least be tolerant to it. These complexes are active photocatalysts when you pair them with a chromophore. The iron complexes are good candidates for surface immobilization. As you saw, we've been able to actually do that at this point. And also, it is very important that we take care of our fossil fuels, because if we don't, I need goggles. There we go. If we don't, they're going to be gone in a flash. We're good. All right. Didn't break Sadler. Okay. So now for the most important part of the talk. These are the heroes behind this work. These are the people that are why I'm here. The greatest part of my job is working with these talented undergraduate students and graduate students at William and Mary. And these are the folks that deserve all the recognition and all the praise, who did a lot of that earlier work. Caroline Margonis did a lot of the work with the immobilizing things onto carbon surfaces. Zach Schiffman did a lot of electrochemistry. Carolyn did a lot of the early work on photochemistry. She did such an amazing job. Ryan Duricio did a lot with electrochemistry. Jess did a lot with photochemistry, as did Megan. Nick worked on the TiO2 project with Megan and Brett. Gannon, Catherine, and Catherine were some of my earliest lab members. Catherine Mayer was the one who came up with the EDM ball spinner, and she's just a very, very fantastic student. Catherine Wise is just incredible. She's now working for the National Academy of Science, and it's just, all these people listed here have done such great work on this, and it's just been an absolute pleasure. Of course, the funding agencies that were mentioned at the beginning of my talk, RICO, and currently my group. My research group is still working through a lot of this stuff. We're really excited to get going more on the carbon stuff that I told you about. If you guys want to stand up, a couple of you are in the audience. Jess is my master's student. She's helped a lot with this talk. She's done a lot, and she's brought just a lot of interest and a lot of passion about hydrogen to the group. Ben has already graduated. He graduated early. He's off to UNC Chapel Hill for his PhD. Marissa is in the audience as well. I think that was her first time kayaking, if I'm correct. Yeah, that's correct. That's the chick, Chickahominy. Tim Wells is also a rising senior. Ryan Anderson is here repping the William & Mary Ultimate team. Ian, Jake, Rachel, Jack, and Claire are all newer members to the group. I'm so excited to have them here. I really want to thank the Tack team. I cannot thank them enough. None of this would be possible without them. Steve, Chandler, Jeff, Andrea, Lisa, Jake, Suzanne, Addie, Catherine Strickland. I ninja'd in another Tack member, Tack team, if you didn't notice that. My wife, Professor Catherine Cole, has been an unofficial member of the Tack team. I think she has let every person in Williamsburg know about this talk. I know that she has let every person on Seamus's soccer team know about the talk. Everyone in every grocery store in Williamsburg knows about it. Thank you so much for your support, Catherine, and just your help always. Also, the William & Mary Chemistry Department, all of my colleagues are fantastic. There are several of us working on similar problems. I want to thank Kristen for this nomination in the awards committee, and also that great work on photochemistry that really inspired me with that Fluorescein stuff. Doug Young for being next to me, the office next to me for 10 years and having to endure me, and also helping with the Tack lecture as well. Our chair, Bob Pike, for just keeping everything going, and also I really gotta thank Claudia and Dawn for just helping with everything. You guys are so amazing, all of you. Thank you so much. I want to thank David and EH&S for allowing us to have fire at our talk today safely. That worked out. I want to thank the provost for inviting me, the president, and also family and friends. I'm happy to answer any questions that you may have.
Hi, thank you. I read recently an article about, or an abstract about using iron in the place of platinum in batteries. I'm not sure if you're familiar with that.
I have seen that. I am not a battery chemist.
Okay, I'm just apropos to your
Yeah.
presentation. Thank you.
Yeah. No, thank you for that comment. That's going to be, battery research, like I said, is very, very important. And especially this newer area that's gaining some traction in flow batteries and things like that. It's going to be very interesting to see where that goes.
Do you have any other catalysts that you may want to use in the future for generating hydrogen?
Oh, yeah, I only told you about iron, didn't I? Oh, because we're pumping iron. I don't hate other metals. Actually, as an inorganic chemist, all that means is that I love everything on the periodic table that's not solely carbon, hydrogen, nitrogen, and oxygen. And cobalt, we have a bunch of cobalt systems that are working great. We have a bunch of nickel systems. Those are also really abundant. So I'm really talking about that first row of transition metals. And if I could be just really honest with you, I never thought I'd be working with iron. In my postdoc, I worked with Rich Eisenberg and Pat Holland. Rich was, into cobalt and these things called redox active ligands, and Pat was working on nitrogen fixation with iron. And I was like, Pat, I'm never going to touch iron. And what freaked me out about iron is, in water, iron's got all this one-electron Fenton chemistry that we're all so familiar with, and I was afraid of that, but it's worked out for us. But yes, we have other metals that we're investigating as well. We do not have tunnel vision when it comes to that, for sure.
Okay, thank you.
This is more a realization than a question, but I was listening to something about fossil fuels the other day, and at the end, there was a list of dozens and dozens and dozens of things that we use and depend on every single day that are manufactured from petroleum.
Oh
and if
my
we're
gosh.
burning it, we will not have it. And I don't think the common layperson like me is really aware of that
Yeah.
as much as we need to be.
Thank you so much for that. That is something that I had intended to mention. That is one of the reasons why I'm referring to these things as so precious. Without petroleum, you don't have a smartphone. Without petroleum, you don't have those seats. We make so many commodity chemicals, so many polymers, pharmaceuticals, and things like that from petroleum. And I always sort of joke with my students, and I say, imagine you're an alien from a different planet, and you come down and you land on this planet, and this planet has this precious resource that we're using for so many things in our daily life, and we're just burning it. What do you think of us? You think, dude, you could be doing this some other way, because getting that petroleum back takes quite a while. So that's an excellent point. Thank you so much for bringing that up. I totally agree with you.
Right, so as we said, the more common metals are needed to scale up for this to actually be industrially useful. But how do the metals like iron and cobalt and nickel compare just in terms of efficiency and yield to the rare earth elements?
Not well to platinum. Platinum's pretty good at this as a metal. In terms of activity, they're pretty good. The iron in hydrogenase, for example, operates with very efficiently and very actively. It's extremely impressive. So we know that they can compete or outcompete with platinum. But when we're talking about this, and I'm not an economist, It's going to come down to how much you're getting out versus how much it's costing, right? And I think on a larger scale, that more sustainable metals are going to be able to address this problem on a global scale, for sure. Because we use platinum in the same line of reasoning that we just mentioned petroleum. We use platinum and iridium for a lot of really important things. Your catalytic converter has precious metals in it, for example. Also, blue LEDs can often be iridium. There are just a lot of uses for these metals that we really need to have them around.
So is there any possibility of using these more common metals for applications like catalytic converters in the future, or does that have to be platinum?
Sure. I don't know about specifically catalytic converters, but these metals are definitely being investigated for many catalytic reactions, one of the most important industrial reactions, and one of the reasons why I mentioned this and why it's mentioned by the Joint Center of Artificial Photosynthesis is making ammonia from nitrogen. And that seems, when I say it like that, that sounds so boring. But that's how we feed the globe. We need to make fertilizer, and we make it to feed the globe from fixing nitrogen. And we use this thing called the Haber process. And the Haber process uses iron. It uses heterogeneous iron, but at really high temperatures and really demanding conditions, okay, that require a lot of energy. So there's a lot of research in that area, for example, in making new catalysts for that particular reaction, which is arguably one of the most important industrial reactions. So yes, these things are being investigated for so many different applications, but yeah, for sure.
I have a question over here. Trying to articulate this, just sort of the zeitgeist, not just in the chemistry community, but in science and humanity in general. It seems like we often develop products without thinking through the entire life cycle. So you produce something and it works great, but then there's, how do you recycle it or how do you dispose of the waste? So I'm wondering if you can just talk about that a little bit with the work that you're doing. Have you thought about it all the way through the process, the life cycle of the materials, and what the waste products might be and how you might deal with those?
Yeah, so since it's not a fully operational device, I haven't thought so deeply about that. Your question is a good one, and I'm wondering if where it's coming from is there's been a lot of traction about photovoltaics in this way. What are we going to do with our silicon solar cells when they're dead? Are they just going to end up in graveyards like electronics? So this is something that people are talking about. For us with iron, it's going to turn to rust over time. And I can think of several places to put rust. One of them is an area that I did my postdoc. It's covered in it. I'm just kidding. But yeah, I think that's not a question that I can answer right now, since this isn't something that's to market. In terms of thinking it through, I will tell you that I don't like using triethylamine as a sacrificial donor, okay? That can be problematic in a couple of ways. There are going to be byproducts from triethylamine. It is not the most environmentally benign substance. So another area in our group to sort of get at what you're saying is how do we use environmental sources of electrons? And you can do that by looking at dissolved organic matter, things like humic acids as a naturally occurring source of electrons. These are, humic acids are in our rivers and in our streams, and they generate dissolved electrons for those processes. And so that's an area that we're actively looking at. And why we're getting at it is because of that question that you just asked. Thank you very much. Thank you for coming to the Tack lecture.